Hi everyone. So I'm going to be uploading a series of short videos as asynchronous learning material. And these videos are going to cover a few more topics related to functions. And it will be a continuation of where we left off in the lecture this week. So with these videos, we'll hopefully be wrapping up functions. And that'll kind of wrap up the review of fundamentals before we launch into the major topics for the course. So let's get started. I'm going to share my screen. Okay, right. So very quickly, a recap of what functions are. So a function is a rule which transforms an input into an output. So if x is the input and f is the function, then f of x, or the value of the function f evaluated at x, is the output. And so function is, very simply put, it's just a rule that transforms a number, an input, into another number, the output. Now, domain of a function is the set of all input values for which the function has a defined output. And just like how you have a set for the inputs, you also have a set to denote all possible output values of the function, and that's the set called range. Now, let's look at a few examples of functions. So I'm looking at the left panel of my screen here, which is the first example, where the function is assigned to any number, its third power. Now, how do I write this function? So here the input is any number, the output is going to be its third power. So I write it here as h of u is u cubed. I could write it as f of x is x cubed. I could say g of y is y cubed. I can write it anyway. So the particular, the letter or the name that I use for the function is immaterial. As long as you get the rule right, you're good to go. Now let's plug in a few arbitrary input values into this and see what values we get. So when h is 1, we get 1. H is minus 3, we get minus 27. And sometimes we may not plug in specific numbers, but we may plug in constants, which could be placeholders for particular values. So here, when h of a is just a cubed, and when I put in the, when I give in the input u plus v into the function h, it's going to give me u plus v the whole cube. And remember, h of u plus v is not u cube plus v cube, but rather u plus v the whole cube. Now, let's look at another example, which is a bit more familiar to economists, where we have a cost function, c of x, which gives us the cost of producing x units of a product. Now we're asked to find what is c of 25. Plug in x equals 25 into the function and find the value, you have the answer. What is c of a? Substitute x with a in the function and you have the answer. What is c of a plus 1? Substitute x with a plus 1 and then you have the answer. Notice that wherever there is an x, I've plugged in a plus 1. Root x is root of a plus 1. So remember, you don't want to make any mistakes there. Whatever the input is, the whole of that input has to go into, So here, c of x is the function that's given to us. And whenever x is equal to a plus 1, you have to put in the entire value of a plus 1 into wherever x is. So that's how you get c of a plus 1. And now the third thing you want to find is the difference between these two expressions. So we have each of these expressions. I'm just going to put that in here and I find the difference and I write it as this particular expression. Now, what is c of a plus 1 minus c of a? So you are producing, say, a units, that's c of a. C of a plus 1 is going to be the cost of producing a plus 1 units. So now the difference between these two is essentially the incremental cost of producing one more unit. And so that's what that intuitively means. And build up your familiarity with concepts like these, because you're going to hear a lot more of this when you start doing producer theory. And you'll hear about average costs, you'll hear about marginal costs. So it'll all link back to something that looks like this. Now, the next that I have here is to graph a few functions. So how do you graph functions? So you have your input value and you have your output value f of x. So the set of ordered pairs x comma f of x, which satisfy your function. If you plot them in the xy plane, you have the graph of your function. So I've given a couple of examples here where I've plotted g of x is minus 2x plus 4, and I've also plotted another function f of x is x squared minus 4x plus 3. Now this g of x is a linear function, which I'm assuming most of us are now familiar with. So that's fairly straightforward. The second one here, the one that I've drawn for f of x, this is a quadratic function. And quadratic functions, when you plot them, are often going to take the shape of either a u or an inverted u. And those are called parabolas. And you'll see that functions like these will make a lot of appearance in applications, in examples from economics. So start becoming more familiar with functions that have these u shapes. So here, yes, I plotted another function, which is a parabola. Now what I'm going to show you next is graphs of a few important functions, which you're very likely to come across very often. So it's a good idea to become very familiar with these graphs so that, at a moment's notice, as soon as you spot them, you should be able to tell what the graph is actually showing you. So the first is y is equal to x, which is a straightforward function. Straight line through the origin at a 45-degree angle. Y is equal to x squared, which is another u-shaped quadratic function. Now notice how y is equal to x squared is always only on the positive, the non-negative side of y, because x squared is always non-negative. And then you have y is equal to x cubed, which takes something that looks like an S shape, but a slightly inverted S shape. And then you have y is square root of x. Notice that this function is only defined when x is greater than or equal to 0. So that's the domain for that function. Because in the real space, square root of a negative number is not defined. So we stay in the first quadrant here, and I plot out y is equal to root x like that. Then the last two that I have here are y is square root of x. Y is modulus of x, which is just the absolute value. And you'll often hear people referring to this function as the V-shaped function. You see how it's just like a straight V, no curvature there, just a straight V. And then the last one that you have, y is 1 by x. This is another very common function you'll see in economics applications. And this function again is not defined when x is 0. And so the domain is the set of all x values except 0. And then when you plot out the function, it's going to take a shape that looks like that. When x is 1, y is 1, x is 2, y is half, and so on. Just plot a few arbitrary points and map it out. That will help you picturize it better. So I plotted it for both the positive values of x as well as negative values of x. And that's the shape of the function. And something that looks like this is called a hyperbola. So we saw a parabola, then there's a hyperbola. You'll start seeing this more often. Okay. Now, another quick note about what a function is defined to be. So a function will assign for every input only one output. If the function gives you more than one output, then it's not a function. So there's something called the vertical line test with which you can check this. So if you draw a vertical line through the function and it cuts the function at only one point, it is a function. If you draw a vertical line and it hits the plot, hits the curve at more than one point, it's not a function. So in this particular example, the second one, you see that the line cuts the curve at 2 points. So which essentially means that for one input value, I'm getting two outputs. And by definition, that's not a function. And extending the same idea to a circle, if I draw a vertical line through a circle, it's cutting at 2 points. And so a circle is also not a function. Now, I'll just quickly introduce the idea of power functions. We're going to just look at different classes of functions. So power functions is one of them. In fact, the set of graphs that we just saw, all of them belong to the class of power functions. And the general form of a power function is ax to the power r, where your x is raised to a particular constant. And these power functions are defined for positive values of x. And I've written out the reason here. Be sure to review this and understand why we're only acting in the first quadrant. Now, I've plotted out a few different power functions. You see how when r is greater than 1, your functions are all going to lie above the y is equal to x line. And when r is between 0 and 1, they're going to lie below the y is equal to x line. So, and all of these pass through the 1, 1 point. And just generalizing this, if r is between 0 and 1, it's going to take on a shape which, and this is going to lie below your x is equal to y line. So x is equal to y line will be somewhere like that. If r is greater than 0, then you're going to have a steeper line. So the laser pointer here is showing you x is equal to y is x power r is going to be steeper than that. Now, when r is negative, just as was in the case of 1 by x, your graph will take on the shape of a hyperbola. So with that, I'll stop the first video. See you in the next one.